Hi, my name is Kim Yokuno. I am from the Institute of Statistical Mathematics. I'm also a visiting scientist of Riken Center for Advanced Intelligence Project. Today, I'm going to talk about the statistical estimation with integral-based loss functions. Okay, today's talk, it's mainly based on these two archive manuscripts. The first manuscript focuses on the robust density power divergence. This preprint has been uploaded to archive in the last July, and also the second manuscript focuses on the higher order variation regularization of the nonlinear models, including neural network. Okay, in the next slide, I'd like to provide more precise overview of this talk. In the first half of this talk, I'd like to consider statistical estimation using robust density power divergence, which is a robust extension of Kalbach-Leibler divergence. And also, in the last half, I'd like to explain about nonlinear and explain about the higher order variation regularization of nonlinear models, including neural network. In the last half, I'd like to consider the regression problem. So I try to predict the outcome of AI from Xi using the regression function of theta, and we usually consider the nonlinear neural networks. And we also impose regularization on the higher order variation of the regression function to be estimated. As you can see in these two practical examples, the loss functions in these applications include the integral functions. And actually, in practice, to minimize these loss functions, it is quite hard to consider these integral terms. And actually, in many previous studies, people usually consider numerical integration to approximate these integral functions, or people instead consider simple restricted model to calculate these integrals analytically. But actually, some of you may know there exist many good optimization technique, and actually the stochastic algorithms in line with Robbins and Monroe 1951 can minimize these types of loss functions. So actually, so in this talk, we revisit the stochastic algorithms in line with Robbins and Monroe 1951, and we will simply apply the stochastic algorithms of Robbins and Monroe to minimize these types of loss functions. So in this slide, I'd like to emphasize that I do not assert any technical novelty of the stochastic in terms of the stochastic optimization in this talk. We simply apply the existing stochastic algorithm in line with Robbins and Monroe 1951. So the contribution of this study is just designing the stochastic gradient to compute the stochastic gradient descent in line with Robbins and Monroe. So anyway, this is the overview of this talk. Okay, let's go ahead. So this slide shows the outline of this talk. In this talk, in the first half, I will talk about the robust divergence minimization. And in the last half, I'd like to talk about the higher order variation regularization of the nonlinear models, including neural network. So in the first half, I'd like to discuss about robust divergence minimization. Okay, to facilitate the understanding of the robust divergence, in this slide, I'd like to start by explaining the Kalbach-Leibler minimization, Kalbach-Leibler divergence, and maximum likelihood estimation. Okay, in this slide, in this section, we assume that we observe these x1, x2, blah, 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 and xn, and these observations from x1 to xn are assumed to follow the distribution Q, and the distribution Q is usually unknown in practice. And then we want to estimate this unknown distribution Q by using these observations. And we can estimate this unknown distribution Q by using a probabilistic model P theta. So P theta represents, usually the uppercase letter of P theta usually represents the distribution, and the small P theta represents the density function. We typically employ normal model or something like that for this probabilistic model. And then Q hat X represents the empirical distribution defined with these observations. Okay, using these symbols, we can define Kalbach-Leibler cross entropy like this one. the Karabac-Leibler cross entropy is defined by the integral of the log p theta x. So the measure of this integral is the empirical distribution, this one, and then we can expand this big integral analytically, and then we can obtain this term. As you can see, this term corresponds to this term is equivalent to the negative sign of the log likelihood. So we can say that the minimizing Karabac-Leibler divergence is equivalent to maximizing the log likelihood. So we can say that the minimizer of Karabac-Leibler cross entropy coincides with the maximum likelihood estimator, which maximizes the log likelihood, this one. So this is a standard explanation of the Karabac-Leibler divergence and the maximum likelihood estimation. So actually, the maximum likelihood estimation is a standard theory, standard method to estimate some parameters in statistics. But usually, this maximum likelihood estimator still has several drawbacks. So for instance, it is known that the maximum likelihood estimator is sensitive to outliers. So please look at this figure. In this figure, I first generated several observations from a uniform standard normal distribution. The true density function is represented by this red line. And then we just generated several outliers here. And we combined these two datasets to make a contaminated dataset. Using this contaminated dataset, we tried to calculate the maximum likelihood estimator when we employed a normal density model. Then, as you can see in the black line, the maximum likelihood estimator is, strongly affected by the outliers. So we can examine that the maximum likelihood estimator is sensitive to outliers. So this is a kind of drawback of the maximum likelihood estimator. So to address this outlier issue, robust density power divergence has been proposed. The robust density power divergence, DPD, was proposed by Bass et al. 1998. And the density power divergence is defined as the difference between these two beta cross entropies. Okay, so the beta cross entropy is defined by this formula. As you can see, the first term of the beta cross entropy consists of the sample mean of the beta's power of the density function. And also the second term is the integral of the 1 plus beta's power of the density function to be estimated. And actually, this second term is required to correct the bias of the beta cross entropy. And in this beta cross entropy, we need to specify the hyperparameter beta, and beta should be positive. And usually, or typically, we employ a beta equals 0.5 or beta equals 1. So this, okay, so, and then it is also known that the density power divergence, DPD, reduces to the Karabac-Leibler divergence if beta reduces to 0. So we can say that the density power divergence is an extension or generalization of the Karabac-Leibler divergence. Okay, and then we can define the beta estimator as the minimizer of the density power divergence, and it is equivalent to the minimizer of the beta cross entropy. So we can define the beta estimator as the minimizer of the beta cross entropy. So these are the definitions of the density power divergence, beta cross entropy, and beta estimator. And then it is known that the beta estimator is robust against outliers. Okay. In the next slide, I'd like to explain why this DPD, density power divergence, and beta estimator are robust against outliers. So to explain the robustness briefly, here I'd like to assume that the X is an outlier included in the dataset, and then we can say that the true density function at the point of outlier should close to 0, right? But even if even for this point, each term in the density power divergence is bounded. But on the other hand, each term in Karabac-Leibler divergence at the outlier point, it's unbounded, because if we insert the very small value into the log function, then actually this term can be unbounded, right? So sometimes the curvature divergence can be unstable if the outlier is included in the dataset. So this is the main reason why the curvature divergence is sensitive to the outliers. Density divergence can simply ignore these outliers. Okay, so this is a brief explanation about why the density divergence and beta estimator are robust against outliers. And you can observe the robustness of beta estimator by using some numerical experiments. So please look at this figure. In this figure, I generated several observations from a standard normal distribution. And also we generated several outliers here. And then we computed the maximum likelihood estimator by using the contaminated dataset. And then, as you can see, the black line, the maximum likelihood estimator, is sensitive to the outliers. And please also look at this colored line, this one, colored line. The colored line represents the beta estimator using a small beta. So yes, this one is a beta estimator. So this one is more robust against maximum likelihood estimator. But as I explained earlier, the density per divergence reduces to the curvature divergence if beta reduces to 0. So the beta estimator using a small beta behaves similarly to the maximum likelihood estimator. But please look at this dot figure, the dot line. The dot line represents the beta estimator using larger beta. And as you can see, if we increase the value of beta, we can estimate the underlying true model very well. So we can see that we can observe the robustness of the beta estimator against outliers here. So this is the simple numerical experiment. So beta estimator is robust against outliers, and I think beta estimator is a good estimator, but usually there exists a computational difficulty. There still remain computational issue. Okay, so please look at this definition of density per divergence again, beta cross entropy again. And then, as you can see, the first term of the beta cross entropy is the finite summation. So actually, this term is, how to say, computationally tractable, computationally feasible. But on the other hand, the second term is the integral of the 1 plus beta's power of the density function. So actually, this term is computationally intractable when we want to minimize the beta cross entropy. So when I started this study, I investigated many previous studies thoroughly, and I found that almost all of the studies that minimizes the robust density per divergence considered as a normal distribution. And actually, if we employ a normal model, normal densities, then we can expand this integral analytically. So for instance, if we employ a univariate normal distribution, then we can expand this integral analytically, and then we obtain this term. So if we can expand this integral analytically, then we can apply a gradient descent, a Newton-Raphson, or some other classical optimization techniques. But yeah, as you know, there exist many non-normal densities in the world. So I was not sure whether we could generalize this computation to non-normal models. Okay, so in this slide, I'd like to discuss about the density per divergence using non-normal densities. Okay, so I investigated several previous studies, and then we can find that only a few studies try to minimize the density per divergence beta cross entropy for non-normal models. So for instance, Jones et al. Tried to minimize the beta cross entropy density per divergence for exponential models, and Juarez and Shukani tried to minimize DPD for generalized Pareto distribution, and Bass et al. Tried to minimize density per divergence for Weibel distribution. And I also heard that recently a Japanese group is trying to minimize the density per divergence for log normal distribution density or something like that. So yes, this is a wind rumor, but anyway, there exists a group now trying to minimize DPD for log normal distribution. But actually, these for distributions densities, we can expand this integral analytically, but yeah, there still remain many non-remaining densities. So to address this issue, so few studies try to minimize the remaining distributions. So for instance, Fujisawa and Eguchi tried to minimize the density per divergence for Gaussian mixture model using the Gaussian model, but actually this study do not minimize the dp directly. This one tries to minimize the upper bound of the density per divergence. And Poisson, the Kawashima and Fujisawa tries to minimize the density per divergence for Poisson distribution using a finite approximation. And actually, there is several approach that minimizes the DPD for the approximation of the density per divergence. But actually, there has no concrete approach. There's no approach to minimize DPD, general approach to minimize DPD for general models. So the problem still remains. So our problem is that what can we do if the observations follow a remaining distribution, like inverse Gaussian distribution or something like that. So for instance, if the observations follow inverse Gaussian distribution, and if we have already known that the observations follow some remaining distributions, then even if we know that the observation follows some distribution, we cannot minimize density per divergence currently, right? So due to the computational limitation. So we are now facing the inevitable model misspecification. And I think that this inevitable model misspecification directly contradicts to the concept of robust estimation. So I thought that this was the problem. Okay. So in this study, I'd like to provide an optimization approach to minimize the density per divergence for general parametric density models. So for instance, in this slide, I'd like to show complex density as an example, and the density function is like this one. And then, as you can see easily, it is quite hard to expand the integral analytically for this complex density function. But yeah, this slide shows the numerical experiments using our proposed approach. And as you can see, if we compute the maximum likelihood estimator using this contaminated dataset, then we can obtain this black line. And this is affected by these outliers. But if we minimize the density per divergence, and we can obtain the beta estimator. And as you can see, the beta estimator, this one, this curve, it's much better than the maximum likelihood estimator. So this is the contribution of this study. Okay. So to explain how to minimize the density per divergence in our method, we can explain about our method in this slide. Okay. So as I explained earlier, our method is a, standard application of the stochastic gradient descent in line with Robbins and Monroe 1951. So I'd like to explain about the classical theories in this slide. Okay, so for simplicity of the explanation, I'd like to minimize the loss function A theta in this slide. To minimize the loss function A theta, usually the Hurwitz gradient descent typically used in the field of statistics, we may update the parameter by substituting the gradient of the loss function multiplied by the running rate eta. But instead of the, in contrast to the Hurwitz gradient descent, the stochastic gradient descent, SGD, tries to update the parameter theta by substituting the stochastic gradient gt theta t multiplied by the running rate eta t. But as long as the stochastic gradient is an unbiased estimator of the gradient of the loss function, then we can prove under some assumptions that the stochastic gradient descent can minimize the loss function. So this is a standard theory of the stochastic gradient descent in line with the Robbins and Monroe 1951. So the most important point here is that we do not need to calculate the exact integral in our problem setting. So for instance, if we want to calculate the Hurwitz gradient descent, then we need to evaluate the integral at first to compute the gradient. But as long as we employ the stochastic gradient descent is only needed to be an unbiased estimator of the gradient. So actually, we do not need to calculate exact integral without evaluating integrals. We can construct unbiased estimator of the gradient. So yes, in the next slide, I'd like to discuss how to construct such a good stochastic gradient for minimizing the density divergence. Okay, so in this slide, at first, in this construction, I generate several random numbers from y1 to ym from the proposal density p tilde p at the iteration t. The proposal density is arbitrary. So for instance, we can employ a normal distribution or something like that. And then we can define the stochastic gradient like this one. So the first term is a simple, is a gradient of the first term in the density divergence. This is a simple one. Yes, there's no device. And the second one, it's a bit complicated. Yeah, we define the stochastic gradient of the second term, integral term by this one. And actually, if we take the expectation of the stochastic gradient with respect to these random numbers, then we can obtain that the expectation coincides with these terms. And actually, these terms coincide with the gradient of the density power divergence. And actually, so what we want to say here is that we can minimize the density power divergence by conducting a stochastic gradient descent using this stochastic gradient. Okay. And actually, similar approach can be found in several existing studies. So for instance, the similar approach can be found in contrastive divergence proposed by Hinton et al. 2002. And as I explained earlier in the very beginning of this talk, I do not assert any technical novelty in terms of the stochastic optimization in this talk. So the contribution of this talk is just a construction of the stochastic gradient to minimize the density power divergence for to minimize the density power divergence. So yes, our contribution is just an application of the stochastic gradient descent. Okay, anyway, I could define the stochastic gradient and then we can minimize the density power divergence. And also, the most important point here is that this stochastic gradient descent is defined with arbitrary m. So for instance, if we employ m equals 1, so it's okay. So m equals, even if m is equal to 1, this stochastic gradient is unbiased estimator. So we do not need to, how to say, draw many random, we do not need to sample many random numbers from the proposal distribution. Only a few samples is okay. Okay, anyway, we can minimize density per cross entropy. So this slide shows the illustration. Okay, so as I explained earlier, we can expand the integral for normal densities. So we can calculate the exact density per divergence and density per cross entropy for normal distribution. So we monitored the values of density per cross entropy. Okay, so the x-axis represents the number of iteration of the stochastic gradient descent, and y-axis represents the density per cross entropy. And as you can see in these slides, in these figures, for all settings, for instance, beta equals 0.1, 0.3, 0.5, and m equals 3, m equals 10, m equals 100, for all settings, we can observe that the stochastic gradient descent minimizes the density per cross entropy. So yes, this is illustration. Okay, so this is the result of the normal case. As you can see, the beta cross entropy, beta density, it's much better than the maximum likelihood estimator. Okay. Okay, this slide shows a non-normal case. For instance, if you employ an inverse Gaussian density, the density function of the inverse Gaussian density is like this one. And actually, yeah, it's quite hard to calculate the integral of the beta's power of this density function. But even for such computationally intractable models, the beta estimator, we can obtain the beta estimator by using the proposed method, and then the beta estimator is much better than the maximum likelihood estimator, which is sensitive to outliers. Okay, so this is the numerical result. Okay, so this slide shows the summary so far. In the first half of this talk, I explained about the first archive manuscripts. And historically speaking, previously, the normal density and some few parametric models are considered in the field of robust divergence. But this study applied a stochastic optimization approach to minimize DPD for arbitrary general models. And actually, stochastic approach has been studied for more than 7 years, originated from the Robbins and Mono 1951. And also there are many theoretical and practical studies for stochastic gradient descent. So we do not assert any technical novelty in the stochastic gradient descent in the field of stochastic gradient descent. So we just proposed a concrete construction of the stochastic gradient for minimizing the density per divergence. And also the similar approach can be found in contrastive divergence proposed by Hinton et al. 2002. And actually, the gamma divergence proposed by Fujisawa and Deguchi 2008 can be minimized in a similar way. Yes, so but actually, we do not skip the technical details. So if you are interested in this minimization, please look at this archive manuscript. Okay, so at last, I'd like to thank Atsushi Nitanda, Hironori Fujisawa, Shintaro Hashimoto, Takayuki Kawashima, Takahiro Kawashima, Kazuhara Harada, and Keisuke Yano for helpful comments. Okay, so this is the end of the first half of this talk. So okay, let's go ahead. So we do not have enough time left. So anyway, yes, in the second half, I'd like to explain about the higher order variation regularization of the nonlinear models, including neural networks. Okay, so at first, I'd like to explain about the motivation of this study. Okay, so nowadays, people start to utilize many nonlinear models, including neural networks, generalized additive models, or deep neural network, or something like that. So these nonlinear models are usually highly expressive. Actually, as you may know, highly expressive models have several problems. So for instance, highly expressive nonlinear models may overfit to the dataset, and also the parameter estimation of the highly expressive models may fall into a local minima. So please look at this figure. So yes, I think this figure is a kind of exaggerated example, but anyway, sometimes if we train a neural network by using this kind of observations, then we may obtain this kind of regression curves. So as you can see easily, this curve falls into a local minima, and then yeah, the obtained curve is a bit complicated because this curve has many inflection points, right? So the motivation in this study is to obtain a simpler curve when we train the nonlinear models like this one. Okay, so this is the motivation. So we want to obtain a simpler curve when we consider a regression problem or something like that. So to address this issue, we introduce higher order variation regularization, HOVR. For the simplicity in this section, we assume that the function f, regression function f, is smooth, and the domain of the regression function f is a compact set. And then we define the KQVR by this function, the integral of the q's power of the case derivative of the function f. And actually, the function fkx represents the case derivative of the regression function fx to be estimated. So fx is a regression function. Okay. So please look at these two figures, these two examples. So as you can see, the left curve is a bit complicated, complex, right? And also the right curve is simpler than the left one, right? So yes, and also for these curves, for the left curve, the second order derivative is actually large. So if we calculate this term for this curve, then we obtain the value 197. But on the other hand, the second order derivative for this simple curve is small. So if we calculate this integral for this curve, we obtain the value 0.64. So actually, this term represents the complexity of the regression function to be estimated. So we can, if we minimize this higher order variation, then we can obtain simpler curve. It is expected that we can obtain simpler curves. Okay. And also, usually the 1,1VR is also known as total variation regularization in many previous studies. Okay, so let's go ahead. So we can utilize this higher order variation regularization to obtain a simpler curve. And then in this slide, I'd like to consider a loss function using this KQVR. Okay, so we just incorporate the higher order variation regularization into this regression loss function. So we define the regularized loss function by the sum of these two terms. Okay, so by following the same procedure as what we did in the robust divergence minimization, we can to say construct a stochastic gradient for this regularized loss function. So in this construction, we first subsample mini batches from the observations x and y, and actually the mini batch is represented by tilde x and tilde y. And then we define the stochastic gradient of the first term by this term. And also we pick up some random numbers from the uniform distribution over the region omega. And then we define the stochastic gradient of this integral term by this term. Okay, and then if we take the expectation with respect to the mini batch and these random numbers, we can say that the expectation of this stochastic gradient coincides with the gradient of this regularized loss function. So we can say that the stochastic gradient descent using this stochastic gradient minimizes this regularized loss function. So we can minimize this term very easily by using stochastic gradient descent. Okay, this slide shows a demonstration. So in this demonstration, I employed one hidden layer perceptron using 50 hidden units. And also this perceptron is activated by the hyperbolic tangent function. I employed same optimizer, same setting, except for the regularization to train neural networks for these three figures. Okay, so please look at the left one. The left one shows the neural network perceptron trained without any regularization. So as you can see, the trained result falls into a local minima, and then you can see that the obtained curve is a bit complicated. But if we impose a parameter regularization, like a ridge regularization, then as you can see, we obtain a simpler curve compared with without regulation. But actually, this one still has many inflection points. So I think that this curve is still complex. But on the other hand, if we employ a proposed approach, then we can obtain this simpler curve. So yes, this one is obviously simpler than these two curves. So I think the proposed higher order variation regularization is effective to train a neural network smoothly, simply. Okay, so from here, I'd like to show some experiments. So this slide shows the experimental results for linear case. I mean, if the underlying true function is linear, then the neural network trained with the ridge regularization is like this one. Yeah, so it has many inflection points. But on the other hand, if we regularize the third order variation of the neural network, then we can obtain this curve. I think this curve is much simpler because it does not include such many inflection points. And also, this result shows the quadratic case. Yes, so that yes, the proposed approach is simpler than the ridge regularization. And this slide shows the case of cubic function. So yes, if we regularize third order variations, then the proposed approach is the neural network trained with proposed approach is simpler than the ridge regularized neural network. So these are the results. Okay, so at last I'd like to discuss which variation order should be regularized to train nonlinear models. And yes, these figures show the results when we regularize the first order variation, second order variation, and third order variations. And actually, if we regularize the first order variation for the regression function, then the regression function gets close to a piecewise constant function. And yeah, also as you can imagine that if we regularize the second order derivative, then actually the obtained nonlinear model gets close to a piecewise linear function. Yes. And actually, and also the numerically speaking, I think that now I'm now thinking that the regularizing higher order variation like third order variation seems better for me as compared with regularizing these lower order derivatives. And actually, in many previous studies like total variation regularization, people regularize the lower order variations. But yeah, as I explained earlier, I think that the higher order variation regularization seems better than these regularizations for lower order variations. Okay, so this is the result. So I think that the higher order variation regularization is better than the total variation or some other remaining regularizations. Okay, so this slide shows a summary so far. So in the last half of this talk, I explained about the second manuscript, second archive manuscript, and I applied stochastic algorithm to minimize the regression loss function equipped with the higher order variation regularization. And also, actually, there exist many existing studies even in the field of statistics. So for instance, we can employ spline regression to obtain a simpler curve for regression problem. But actually, we can implement this stochastic algorithm very easily, even for recent neural networks. So I think that the ease of the implementation is a kind of advantage for our approach. And also, our approach can be simply generalized to different problems like classification or something like that. Yeah, we can simply replace the loss functions. And also, we can simply generalize this approach to the multivariate case. So for instance, actually generalizing the spline regression to the general multivariate case is quite difficult. Actually, yes, we can do that, but it's quite difficult to implement. And also, it's quite hard to follow the theories. So yes, our approach is very simple. Yeah, we can generalize approach to multivariate case very easily. So I think this is a good point for our approach. And also, yeah, we think that regularizing the higher order derivatives seems better than penalizing the lower order derivatives. Okay, so this is a summary so far. Okay, so in this slide, I'd like to conclude this talk. Okay, so yes, in this talk, I talked about the minimization of the robust density divergence and the higher order variation regularization for nonlinear models. So yes, this is the conclusion. Thank you very much for listening.